Tuesday morning, late October, maybe 41 degrees and a wet fog hanging over the lot. A 2011 Nissan Altima 2.5S rolls into my bay with 118,000 miles on it and a guy behind the wheel who's already done with the whole situation. He's not mad at me yet. He's mad at the last two shops. He hands me a folder, an actual folder with receipts in it. $340 at the first place for a brand new mass airflow sensor. A quote for $610 at the second place for a fuel pump they swore was the problem. And the car still does the thing. The thing being this: he pulls away from a stop sign, gives it light throttle, and for about half a second the engine just goes dead. No power, a little shudder. Then it catches and pulls fine like nothing happened. Worse when it's cold, worse when it's damp. Comes and goes. Some mornings it doesn't do it at all, which is exactly why the first shop couldn't reproduce it, and the second shop started guessing. Here's the part I want you to sit with for a second, because it's the whole video. The mass airflow sensor they replaced for $340. Nothing wrong with it. The original one was fine. The new one was fine. Both of them were reading the air just like the engineer designed them to. The problem was 4 inches away from the sensor, in a place neither shop bothered to look, and it would have cost this man somewhere between $0 and $25 to fix. I found it in about 4 minutes with a tool that costs less than a tank of gas. And I'm going to show you the exact test, because once you know it, you will never get talked into a parts cannon again. That hesitation when you hit the gas, that little flat spot, that stumble, that half second where the car seems to forget it has an engine. Most people chase it for months. They replace sensors. They replace the fuel pump. Some of them replace the whole throttle body. And the real culprit, more often than any of those, is a connector. One dirty, corroded, slightly green electrical connector. That's it. That's the boogeyman. Let me tell you how I know, and then let me tell you why it happens. Because the why is the part that's going to save you real money on whatever you're driving right now. So I've got the Altima up. First thing I do is not grab a scan tool. First thing I do is talk to the guy, because the symptom tells you more than the codes do half the time. He says it's a quick dead spot off the line. Not a misfire feeling, not a buck and surge like it's running out of fuel up high. A clean little nothing right when he tips into the throttle. That detail matters. A misfire feels rough. This felt like a pause. Those are two different failures, and they live in two different parts of the car. Now I plug in. I'm not looking for a stored code first. I'm looking at live data. I pull up the mass airflow reading in grams per second, and I watch it at idle. Healthy too. 5-liter 4-cylinder at warm idle should sit somewhere around 3 to 4 grams per second, give or take. His is sitting right there. Looks perfect. Which is exactly why the first shop thought the sensor they put in fixed it. At idle, everything's calm. The signal's clean. The car runs like a sewing machine. The failure doesn't live at idle. It lives in the transition. So I do the thing the manual won't tell you to do. I reach in, and with the engine running, I grab the wiring harness right at the MAF connector, and I wiggle it, gently, side to side, a little tug, a little flex where the wires go into the plug, and I'm watching that grams per second number the whole time. For about 3 seconds, nothing. Then I flex it one specific way and the number jumps. Spikes to 40, drops to 0, jumps again. The engine stumbles on the bench just sitting there. There it is. That's your half-second dead spot, reproduced in my hand, on demand, with the car not even moving. That's the 4-minute test, the wiggle test. I'll come back to why it works in a second, because I want you to understand it, not just copy it. I unplug the connector, and there it is, green. One of the terminals has that crusty, powdery, blue-green corrosion on it, like a battery terminal in miniature. The female pin inside the plug has lost its spring. The metal's gone dull and pitted where it should be shiny. This connector has been quietly failing for probably 2 years, and every shop that opened the hood looked right past it, because the sensor it feeds was brand new, and the assumption was, new sensor, problem solved. I noticed a long time ago, after seeing this exact failure on more cars than I could count, that nobody suspects the connector. Mechanics suspect the part. The part is the expensive thing. The part is the thing with a name and a part number. The part is the thing that shows up in the labor guide. The connector is just the thing the part plugs into. It's invisible, and that's exactly why it eats people alive. Okay, here's the physics, and stay with me, because once this clicks you'll understand every electrical gremlin you ever have. A mass airflow sensor is a beautifully simple idea doing a brutally hard job. Inside that plastic housing is a tiny heated element. On the Nissan, on most modern cars, it's a hot film, a little platinum film, But the principle goes back to the hot wire sensors of the late 80s. The computer heats that element to a set temperature, usually a couple hundred degrees above the incoming air. Then air rushes past it as you drive. Moving air pulls heat off that element, the same way wind chill pulls heat off your skin. The more air, the more cooling, the more current the computer has to push to keep the element hot. The computer measures that current and translates it directly into how much air, by mass, is entering your engine right now. That number is the foundation of everything. Fuel, timing, all of it gets calculated off how much air came in. Now think about what that signal actually is. It's a small electrical signal traveling on thin wires through a connector and into the engine computer. Tiny voltages. Precise. The computer is reading this thing hundreds of times a second and trusting it completely. So what happens when the connector corrodes? The corrosion is an insulator. That green crud, that oxide layer on the pins, it's not metal anymore. It's basically a tiny crust of resistance sitting in the path of your signal. And resistance does two ugly things. It drops the signal, so the computer reads less air than is really there. And worse, when it's intermittent, when that loose corroded pin makes contact and loses contact as the engine rocks on its mounts and the harness flexes, the signal doesn't just read low. It glitches. It spikes and drops and lies. Here's the analogy that makes it stick. Picture you're on the phone with someone and the line keeps cutting out. They're trying to give you a number. They say, "Give me 400, but you hear, "Give me 100. So you guess. You give them 100. That's your engine computer. The MAF says a big slug of air just came in, add fuel now. But the corroded connector chops the message, and the computer hears half of it, and it adds half the fuel. The cylinder gets a lean shot of mixture for a fraction of a second. Lean mixture doesn't burn well. The engine stumbles. Then the connection comes back, the message gets through, the fuel catches up, and the car pulls away. Half a second of dead spot. Exactly what the guy described. And it lives in the transition because that's when the air is changing fastest. At idle, the airflow is steady, the message is short and simple, even a bad line can carry it. The instant you tip into the throttle, the airflow spikes, the message gets long and urgent, and that's when the broken line drops the most important part of it. That's why your car runs fine until the exact moment you ask it to do something. You won't find the wiggle test in the owner's manual. You won't find it in most repair manuals either. It exists in the heads of guys who've been burned enough times to stop trusting the part and start suspecting the path. Now let me widen this out, because this is not a Nissan problem, and I don't want you walking away thinking you're safe because you drive something else. I've seen this exact failure on a 2008 Chevy Silverado 1500 with the 5.3. Owner came in convinced it was the transmission because the truck would shudder on light throttle around 40 miles an hour. It wasn't the transmission. It was a corroded ground on the engine harness messing with the MAF reference. I've seen it on a 2010 Honda Civic that a guy had taken to 3 shops, and on Civics it tends to show up as a slightly different symptom, a little surge at cruise, because Honda's fueling strategy reacts to the bad data differently than Nissan's does. I've seen it on a 2012 Volkswagen Jetta 2.5 where the connector itself was fine but the harness had a green, corroded section 6 inches upstream where water had wicked into the insulation and rotted the copper from the inside, which is a nastier version of the same disease. And here's a cross comparison that'll change how you think about this. Not every car even has a mass airflow sensor. A whole bunch of engines, a lot of older Chryslers, a lot of GM trucks, basically every turbo car running what's called speed density. They don't measure airflow directly at all. They calculate it from the manifold pressure sensor, the intake air temperature, and the engine speed. No MAF connector. No MAF problem. So if your buddy with the Hemi tells you he's never heard of this, that's why. His car doesn't have the part. Yours might. The two systems fail in completely different ways, and a mechanic who learned on one and doesn't think about the other will chase his tail on your car all day. Why did the industry go this direction in the first place, with all these sensors and all these connectors? Because of the rules. In 1996, OBD2 became mandatory on every car sold in the United States. Standardized codes, yes, but more than that, it forced manufacturers to monitor everything. The computer now had to watch the airflow, cross-check it against the oxygen sensors, flag a fault the instant the math didn't add up. To do that, you need more sensors. More sensors mean more wires. More wires mean more connectors. And every single connector is a place where copper meets copper and air and water and salt eventually get in. The car got smarter and more honest, and the price of that was a few dozen new little spots that can rot. Then around the early 2000s, drive-by-wire showed up. They took the cable that used to run from your gas pedal to the throttle, and they threw it in the trash. Now your pedal is a sensor, the throttle has its own sensor, sometimes two for redundancy, and they all talk to the computer over wires. More connectors. Toyota, to their credit, built a lot of redundancy into their throttle sensors, two signals that have to agree, so when one drifts the computer catches it and throws a specific correlation code instead of just running bad. Some other manufacturers ran leaner on the safety margin to save a few dollars per car. That's a real engineering decision somebody made in a meeting, and you're living with it 20 years later. That brings me to the other half of this. I've been saying MAF this whole time, but the title says connector, and the connector that does this isn't always on the airflow sensor. The second most common one I find is on the throttle position sensor. The throttle position sensor, the TPS, does for the throttle what the MAF does for the air. It tells the computer how far open the throttle is. Older ones are a potentiometer, basically a volume knob, a wiper sliding across a resistor, putting out a voltage that climbs from around half a volt at closed throttle to 4.5 volts at wide open. Newer ones are contactless, but they put out the same kind of climbing signal. The computer watches that voltage to know, instant by instant, how hard you're asking for power. Now here's where the connector corrosion does its dirtiest work, and it ties back to something I mentioned that I want to close the loop on. Remember I said the MAF gives a clean signal at idle and only lies during the transition. The TPS is the transition. When you tip into the gas, there's a moment where the air responds faster than the fuel can. The fuel has to travel, it has to atomize, some of it wets the intake walls. So there's a built-in lean spike every single time you open the throttle, for a fraction of a second. The engineers knew this. They built in a fix. It's called acceleration enrichment, and it's the digital version of something carburetors did mechanically for 70 years. Old carburetors had an accelerator pump, a little squirt of raw fuel that fired every time you stepped on it, to cover that lean spike. Step on an old carbureted car, and you could hear it, almost a little cough of richness. Modern computers do the same thing electronically. The instant the TPS voltage starts climbing, before the airflow even fully catches up, the computer fires an extra shot of fuel to cover the transition. That squirt is timed off the throttle sensor. So now picture a corroded TPS connector. The voltage signal is the trigger for that fuel squirt. If the connector adds resistance, the voltage offset shifts, and the timing of the squirt gets sloppy. If the connector is intermittent, the signal glitches right at tip-in, and the squirt either fires late or doesn't fire at all. And what do you get when the acceleration enrichment fails to cover the lean spike? A dead spot, a stumble, a hesitation, the exact same symptom as the bad MAF connector, coming from a totally different sensor for a related but distinct reason. This is why two cars with the identical complaint can have two different culprits, and why throwing a MAF sensor at a TPS problem fixes nothing. That's the second pattern. The MAF connector starves the calculation. The TPS connector mistimes the squirt. Both end up as that half second of nothing under your right foot. Let me give you a real one. A 2013 Ford F-150 with the 5.0, customer's a contractor, drives it loaded all day. Complaint was a hesitation off the line that he'd been told, by a dealer, was a known throttle body issue and they wanted $900 to replace the throttle body and reprogram. $900. He came to me for a second opinion before he signed off. I pulled the connector on the throttle body, and the seal had cracked, and road grime and moisture had been getting in for 2 years. Cleaned the terminals, packed it with dielectric grease, put it back, free. The hesitation was gone, and it stayed gone. He bought me lunch instead, which is the better deal for everybody. The dealer wasn't lying exactly. The throttle body has the sensor in it, so technically a new throttle body would have come with a new connector face, and probably would have fixed it. They just sold him the most expensive possible version of cleaning a plug. The dealer's service department isn't going to walk you through cleaning a connector. Not because they're evil, because of how they get paid. A tech in a flat-rate shop gets paid by the job, not by the hour, and the labor guide pays a fat number for a throttle body replacement and pays nothing for diagnose intermittent connector and clean it. If you were that tech, with a mortgage, which job are you reaching for? The system rewards the parts swap. Knowing that isn't paranoia. It's just understanding how the man across the counter feeds his family. Now, how do you find this yourself? And how do you fix it right? Because there's a wrong way that'll have you back in the bay in a month. Finding it. The wiggle test I described works on both sensors. Engine running, scan tool watching live data, MAF in grams per second or TPS in volts or percent, and you flex the harness right at the connector and watch for the number to jump. No scan tool. You can do a rougher version. Engine idling. Reach in and wiggle each connector and listen for the idle to change. If touching a connector changes how the engine runs, you found your suspect. That's not a maybe. That's a confession. When you pull the connector, you're looking for three things: green or white powdery corrosion on the pins. That's the obvious one. Pins that have spread open and lost their spring tension, so they don't grip tight anymore. And a melted or discolored plastic housing, or a cracked rubber seal, because once the weather seal fails, the corrosion is just a matter of time. Look at the wires too, right where they enter the plug. Sometimes the corrosion isn't on the pin. It's wicked up inside the wire under the insulation, and you'll see a green tinge, or the wire will feel stiff and brittle. That's the Volkswagen failure I mentioned. Now the fix, and here's where most people, including a lot of mechanics, do it wrong. They grab a can of brake cleaner or carburetor cleaner and blast the connector. Do not do that to a MAF sensor. The hot film element inside is delicate, and brake clean will strip it, and now you've turned a $5 connector problem into a $200 sensor problem. You use electrical contact cleaner, the kind made for electronics, CRCQD, or a deoxidizing cleaner like Deox-IT. If the pins are actually crusted, you work them gently with a small brass brush or a pick. You don't gouge them. You let it dry fully. And here's the step almost nobody takes, the one that separates a fix that lasts from a fix that comes back in a month. You pack the connector with dielectric grease before you reconnect it. Dielectric grease is a non-conductive silicone grease, and the reason people get confused is they think, wait, non-conductive, won't that stop the signal? No. The metal pins still touch metal to metal. The grease gets squeezed out of the contact points. What the grease does is fill all the air gaps around the connection so moisture, oxygen, and salt can't get back in. You're not greasing the contact. You're sealing the connector against the thing that caused the problem in the first place. Skip this step and you'll clean the same connector again next fall. If the pins are too far gone, spread out, broken, melted, you don't reuse it. You buy a repair pigtail, which is the connector with a few inches of wire already attached, costs maybe $15 to $30, and you splice it in. Solder and heat shrink, not those crimp butt connectors, because a bad crimp is just a brand new corrosion point waiting to happen. You can see the pattern. Every shortcut in this repair is just a way to recreate the original failure. Now, I told you earlier I'd come back to why this shows up more on some cars than others, and here's the pattern that ties it together. It's geography and it's chemistry. The Rust Belt, the Salt States, the Midwest, the Northeast. Anywhere they dump salt brine on the roads all winter. Eats connectors alive. Salt plus moisture is an electrolyte, and an electrolyte plus two slightly different metals is a battery, and a battery slowly corrodes itself. That Altima from the start of this. Ohio plates. Of course it was. A car from Arizona with the same miles will have connectors that look factory fresh, because the desert never fed them the salt. Same car, same sensor, completely different failure rate, and it has nothing to do with the engineering and everything to do with the zip code. And here's the deeper layer, the thing behind the thing. The terminals in these connectors are usually tin-plated copper. Tin is cheap, tin solders well, tin is fine. But tin oxidizes, and tin is prone to something called fretting corrosion, where tiny vibrations, the constant buzz of an engine, where microscopic movements into the contact and rub the plating away over time, exposing the base metal that then oxidizes. Gold-plated terminals don't do this. Gold doesn't oxidize, period. So why doesn't every car use gold pins? Because gold costs money, and a car has hundreds of connectors, and a few cents per pin times hundreds of pins times millions of cars is a number that makes an accountant flinch. So they use tin, and tin is good enough for the warranty period, and what happens at 120,000 miles in a salt state is, frankly, not the manufacturer's problem anymore. That's not a conspiracy. That's a spreadsheet. But it's the spreadsheet that put that green crust on your Altima's MAF pin, and now you know exactly why it's there. There's one more failure mode in this family, and it's the meanest one because it'll fool the wiggle test, and it'll fool a lot of mechanics. It's the ground. Every one of these sensors needs three things to work: a reference voltage in, usually 5 volts, a signal wire out, and a ground, a return path back to the computer. People obsess over the signal wire and forget the ground. But if the sensor's ground is corroded, the whole reference shifts. The computer thinks 0 is somewhere it isn't, and every reading the sensor sends comes back skewed, even though the sensor and the signal connector are both perfect. I've chased this one on engines where the actual fault was a corroded ground strap bolted to the block, 8 inches from any sensor, and the symptom showed up as a lying MAF. The picture only comes together when you stop thinking about the part and start thinking about the whole circuit. Reference in, signal out, ground back. 3 legs. Any one of them goes bad, and the sensor lies through no fault of its own. Most drivers will go their whole lives never knowing this circuit exists, and they'll buy 3 sensors trying to fix one corroded ground. The sensor was never the problem. The sensor was the messenger, and they kept shooting the messenger. Toyota, by the way, tends to ground their sensors a little more thoughtfully than some, with dedicated returns instead of sharing a ground across the harness, which is part of why a high-mileage Camry will often run clean, where a comparably aged car from another brand has gone gremlin. Honda runs somewhere in between. It's the kind of design detail that never makes a brochure but absolutely shows up at 150,000 miles. That's the difference between a car engineered to be cheap to build and a car engineered to age well, and you find out which one you bought right around the time the warranty ends. So let me put the whole map in front of you. Your car hesitates when you hit the gas. Before you let anybody sell you a fuel pump, a throttle body, a coil pack, or a mass airflow sensor, somebody needs to do the 4-minute test. Engine running, watch the live data, flex the connectors at the MAF, at the throttle position sensor, and check the ground. If the number jumps, you've found it, and the repair is a can of contact cleaner, a tube of dielectric grease, and 20 minutes, or a $15 pigtail if the pins are toast. That's the whole thing. That's the whole thing. That's the repair 2 shops missed on a car that had already cost a man almost $1,000 in parts that were never broken. I went back out and told the guy with the Altima, showed him the green pin under a shop light, cleaned it, greased it, plugged it back in, took him for a drive, made him tip into the throttle a dozen times pulling out of the lot, and the dead spot was gone. Just gone. He stood there holding that folder full of receipts, $340 for a sensor that was fine, a $600 quote for a pump that was fine, and the actual fix had cost him the price of a can of cleaner I had sitting on the bench. He didn't say much, just looked at the folder, then looked at the car, then folded the folder shut and put it in his back pocket. Some things you don't need explained twice. If you want to keep hearing about the stuff the shop would rather you didn't ask about, you know where to find me.